Hello. Hello. So yeah, today we'll start our session. So this is your week 10. Hello. Yeah. So today this is a tutor for your week 10. This is Rahuldev Ghorai from ICT. So yeah, so let's start with our session. Today's topic of discussions will be eigenvalue and eigenvectors, and then we'll do a little bit about the diagonalization. I mean, how we diagonalize matrix and all. Okay. So yeah, to begin with, if you have a matrix, I mean, if you have a matrix, A, let's say, okay, let me start with this. So if you have a matrix A, B, C, D, like this, or let's say it's a 2 by 2 matrix. So then how you compute eigenvalue and eigenvectors of this matrix? So the last weekend we have done the rank of a matrix, but I mean, when you know the rank of a matrix, you know many things about the matrix already. But yeah, so if you know eigenvalue and eigenvectors, then you know like kind of most of the things about the matrix. I mean, many things can be said from the eigenvalues and eigenvectors. So if you have a matrix say A, I mean here it's A is equal to, let's say here, then you make A, you would multiply A with X, a vector, and if you get something like some constant time again X, so this type of relation it holds, then I mean lambda is eigenvalue, and the corresponding eigenvector is X. X is eigenvector. Okay. So so you know this matrix, it can come from let's see, if you have a matrix like this type of matrix with theta, let's say it's cos theta minus sine theta, cos theta. So what is this matrix? This matrix is nothing but a rotational matrix. If you multiply r theta by x, I mean xy, then it will rotate the xy point. If it is xy is here, xy here, it will rotate the point by theta angle. Let's say here it is coming, it will be r theta of xy. So for all the values of theta, like if you like have a point, so let's say how you evaluate for this one, how you evaluate the lambda, I mean the eigenvalue. To do this, what you have to do, this r theta is a matrix, and you make r theta minus lambda times I. That determinant has to be 0. I mean, for why I'm telling this, so we have ax equal to lambda x, right? When you have x equal to lambda x, from there you want to find a eigenvector x, you have to find a solution of this system, which is a non-zero solution. So what does that give? This a minus lambda I times x has to be 0, and x is non-zero. X has to be non-zero. To prove that x is non-zero, like to get a non-zero solution, 0 is always a solution, but to get a non-zero solution, a minus lambda I of the determinant of this has to be 0, and from there you can get the value of lambda. Here also we are doing same, r theta minus lambda I is equal to 0, and then what we get is cos theta minus lambda minus sine theta, is determinant of this, and then 1 minus sin theta cos theta. That is equal to 0. That implies cos square theta minus cos theta lambda, sorry, minus lambda. So this cos square theta minus cos theta lambda and minus 2 cos theta lambda plus lambda square plus sin square theta is equal to 0. That implies your lambda square minus 2 cos theta lambda plus 1 has to be equal to 0. And that implies lambda will be 2 cos theta plus minus square root of 4 cos square theta minus 4 over 2, right? So sin square theta plus cos square theta is equal to 1. So this will be cos theta plus minus I sin theta. I mean, even for this type of matrix, you see for all cos theta, you cannot find a real value of a real eigenvalue. I mean, for the theta, if theta is equal to 0, I mean n pi, then only it will be 0. Otherwise, you cannot find lambda. If theta is not equal to n pi types, then you cannot find a real lambda such that x equal to lambda x will happen. I mean, it is not always true, and it is not always true for any vector also. Okay. So, I mean, the eigenvalue or eigenvector is the vector of the if x is of eigenvector of A, if uh, after multiplying by ax is in the same direction of x, right? So then only, I mean, then only it will happen that x equal to lambda x, or you can say in 2 dimension, or like they are dependent, linearly dependent, right? So yeah, so this is eigenvalue and a little bit about eigenvalue and eigenvectors. So when you have in for general matrix, if you have eigenvalue a is a matrix, and you have eigenvalue lambda and corresponding eigenvector is x, then what will happen? And you have lambda corresponding to lambda, you have one x. So corresponding to lambda of 1, if you have x1 and corresponding to lambda 2, let's say you have x2, and this is called, let's say, 2 by 2 matrix. So then x1 is a eigenvector, you can write like x11, x21, and this will be x21, sorry, x12, x22. Then what you can write, this p you can write as x11, and then what will happen? This, I mean, before this p constructing p, this they will be linearly independent. So if lambda 1 not equal to lambda 2, then of course it will be linearly independent. Even though lambda 1 equal to lambda 2, they might be linearly independent or dependent. Okay. So as they are linearly independent, you can make this matrix which will be invertible. And when invertible, so then, and if P is invertible, you can write P inverse AP. P inverse, you can, P inverse exists, and if you multiply P inverse to A and then multiply by T, then this will be diagonalized. Like, this will be a diagonal matrix. So if this happens, I mean, this in this case it will happen, but if it's always happen that P inverse AP is equal to D for some P, then A is diagonalizable. Okay. And we say a characteristic equation of a matrix is this A minus lambda I. The determinant of this is equal to 0. It will be a polynomial. You will see it will be a polynomial in lambda, like we saw. This is called characteristic equation. Okay, so this is a characteristic equation of the uh, matrix A. So if A is n by n matrix, then we will have n number of values of lambda. Let's say you start with the matrix. Let's say if you have like 0, 0, 2, 0, 2, 0, 2, 0, 3. So here I will show that how you evaluate eigenvalues. So what you do, A minus lambda I, determinant of this has to equal to 0, then determinant of this will be A minus lambda will be 0 minus 1, 0, this will be 0, this will be 2, 0, 2 minus lambda, sorry, it's lambda, 2 minus lambda, 0, 2, 0, 3 minus lambda, that equal to 0. That implies if you did this, this will be minus lambda 0, 2, 0, 2 minus lambda 0, 2, 0, 3 minus lambda. Okay, that equal to 0. That implies now you know how to like factorize this. I mean 2 minus lambda times 3 minus lambda, right? And then plus 2 times uh, minus of 2 times 2 minus lambda. That would be equal to 0, right? So what will happen then if you take 2 minus lambda common from both sides, it will be and negative of 2 minus lambda, let's say negative of 2 minus lambda you take common, then what will be this 3 lambda minus lambda square. Negative of 2 minus lambda you have taken common, so it will be plus 4, right? That equal to 0. That implies 2 minus lambda times lambda square minus 3 lambda minus 4 is equal to 0, right? That implies 2 minus lambda lambda, it will be, you can, if you see this, it will be lambda minus lambda square minus 3 lambda minus lambda minus 4 is equal to 0. That's why 2 minus lambda minus 3 and sorry, it cannot be like minus 4 lambda plus lambda. So lambda minus 4 lambda minus lambda plus 1, that is equal to 0. So what are the values of lambda? Lambda is can be 2, lambda can be 4, or lambda can be minus. These three values are possible. So this A matrix we started with, this matrix. This matrix has 3 eigenvalues there, 2, 4 and minus 1. So now the question is how you determine the eigenvector. Okay, how to determine the eigenvector? So your matrix is this 2, 0, 2, 0, 2, 0, 0, 0, 3. Sorry, 2, 0, 3, right? Two, 0, 3, right? And your eigenvectors you got 2, 4 and minus 1. And we have already discussed that each corresponding to each eigenvalue, we will get one eigenvector, right? I mean, at least one eigenvector. So that we'll see. So let's say I want to find. So the question is find. Not case 1, we will find eigenvector corresponding to the eigenvalue 2, okay, of this matrix. So then what will happen? This 2 0 2 0 2 0 2 0 3, you multiply with the vector x. That capital X I am writing as here x1, x2, x3, right? So that has to be equal to some x1, x2, x. I mean that has to be equal to x2 times x1, x2, x3. Because you are trying to find out a eigenvector corresponding to 2. That's why these two is coming into the picture here, right? These two because of these two. So then how? Then now you know how to solve it, right? I mean you can solve in the like way you want. So I mean the first thing will be this one you can write as 2x1 plus 2x3, and the matrix multiplication, I'm writing matrix multiplication, that will be 2x2 and 2x1 plus 3x3, right? Did I make a mistake? No, right? It's okay. Yeah. So if we do that, then what will happen? And that will be, that has to be equal to 2x1, 2x2, and 2x3, right? The interesting thing is, what if you see this 2x1 plus 2x3 has to be 2x1, and that implies x3 has to be equal to 0. And from second equation you don't get anything, it's trivially true. And for from third equation, right, from third equation what you will get is 2x1 plus 3x3 is equal to 2x3, and that implies x1 is equal to minus x3, but that is equal to minus of 0 is 0, and the x2 value. So this equation, this system is valid for any value of x3, sorry, any values of x2, and you have x1 is equal to 0, x3 is equal to 0, but you have no information about x2, and you can see that x2 is any real number. If x2 belongs to any real number, then it will be solution also. I mean any zero constant 0 where constant belongs to R is a solution of 1, and 1 is your this is 1, let's say. Okay, so 0 C0 is eigenvector, because we started with x1, x2, x3, which is eigenvector, and we found out that this 0 C0 is eigenvector. I mean, it is the solution, and that implies the 0 C0 is eigenvector, right? So 0 C0 eigenvector means this is like you can write like this 0 C0. Okay, this, I mean, this is transpose, and we usually write the eigenvector as 0, at least 1 point for 1 point, this is 0, but anything like 0 half 0 also eigenvector, 0 3 0 also eigenvector, 0 pi 0 also eigenvector, like that. I mean, but what you will say, if you say just eigenvector is 0 1 0 corresponding to lambda is equal to, that is enough, because all of them are linearly dependent. You will say linear. So one of them if you have, then another can be written as the one just multiplication by just scalar multiplication, right? Okay, so can you hear me? Hello? Someone joined. Tanushree. Okay, so no, so anyway, so this is why we'll say this. I mean, this is one of the eigenvalue. So we'll take one eigenvalue. So corresponding to the eigenvalue to the matrix the eigenvector of the matrix is 0, 1, 0. That's enough. But the eigenspace, there is something on eigenspace, that will be nothing but the thing like the generated by, I mean, C times 0, 1, 0. I mean, the vector generated by the space generated by this vector C belongs to R. Okay. Yeah. So this is one eigenvector. Let us compute the eigenvector corresponding to lambda. So I'll show something. I'll show you something. Like some observation. So that's why I'm also again calculating for lambda is equal to -1. Right. So when lambda equal to -1, let's say eigenvector is x1, x2, x3 transpose. I mean not comma, it's transpose. Okay. So then what will happen is 0, 2, sorry, 0, 0, 2, 0, 2, 0, 2, 0, 3 will be, should be nothing but you multiply by x1, x2, x3, that should be equal to x1, x2, x3. And then if you multiply by this, then it should be 2x3. I made a mistake. Yeah, so this should not be 2, 0, 2. This should be 0, 0, 2. Okay. So if that is true, then I mean, if the solution will change. Okay, let me just do it quickly. If it is 0, 0, 2, then 0, 2, 0 and 2, 0, 3, right? That's what we started with. Okay. So 0, 0, 2, then where it will change. So this matrix I made mistake. So 2, 0, 2. So this will be 2x3 only, and 2x3 will be equal to 2x1. Okay, and so that does not imply x3 is equal to 0. Let me just correct it. Okay, as none of you are here, I mean, we while seeing in the, I mean, while watching in the recorded video, so you will understand. So 2x1 is equal to x3 means x1 is equal to x3. I mean x1 minus x3 is equal to 0. And from here again x1 minus x3 is equal to 0 you will be getting, right? Sorry, x1, yeah, x1 minus x3 is equal to 0. And another you get x1 plus x3 is equal to 0, right? So that imply also it is both are 0. x1 is equal to x3 is equal to 0. So anyway you will be getting this is the eigenvector. Okay, so that is not a problem. And here what you get 2x3, 2x2, 2x1 plus 3x3, that has to be equal to negative of x1, negative of x2, negative of x3, right? What does that imply? x1 plus 2x3 has to be 0, 3x2 is equal to 0, 2x1 plus 4x3 is equal to 0. That implies x2 is equal to 0 and x3, sorry, yeah, x1 is nothing but minus of 2x3. So the solution is this type of minus 2x3, 0 and x3. And this x3 can be anything, right? That you can check this type of vector. So minus 2, 0, I mean minus 2, 0, 1 multiplied by constant, this will be a solution of this system. And what you see, the eigenvector corresponding to lambda is equal to 2 was 0, 1, 0, 0, 1, 0. Corresponding to lambda equal to minus 1, the eigenvector is this one. Minus 2, 0, 1. One of them. See, any constant time also you can take. So you will see they are linearly independent. You can just check it like we did in the last class. You can check that they are linearly independent, right? So I mean that's why I gave you earlier. I started with this two evaluating these two, and if you evaluate the eigenvector corresponding to lambda equal to 4, you will get one eigenvector, and you can check that these three are also linearly independent. At least you can, first of all, you can try to find out, try to show that these two are linearly independent, that you can show it easily, and then that is that then observe, then that will be the observation that you can prove for all of three that it's they are linearly independent. So this was kind of a little bit theory about all this, and eigenvalue and eigenvectors, which I wanted to say. And we discuss about reflective reflections in R2. We can show that the reflection in R2 is nothing but diagonalized, is also diagonal. So all those things we will do it later maybe. But before that, let us do some uh, assignment questions which is given. Okay. So this is I'm doing from week 10 assignments a little bit and some other examples also. Okay. Okay, so one question about algebraic multiplicity and geometric multiplicity. Algebraic. So what is algebraic multiplicity and what is geometric multiplicity, and that like of a eigenvalue of an eigenvalue. Okay. So if you have an eigenvalue, so if you have a matrix, then you will have a equation. I mean the polynomial equation, like a characteristic equation, and that will give you solutions. Let's say you have a matrix like this. I mean the 2002. What will be the what are the eigenvalues? Only two, right? Eigenvalue is two, but two occurs. I mean the order of two in the characteristic equation is two, right? So the algebraic multiplicity will be two. Algebraic multiplicity is the highest power in the uh, factorization of the uh, characteristic equation. Okay, I mean if you say it more logically, more in the mathematical. I mean, if you say in the more mathematical way, I mean, the mathematical precise definition of algebraic multiplicity is the number of times an eigenvalue appears as a root of a characteristic polynomial. These two appears twice in the root of the characteristic polynomial. So uh, the algebraic multiplicity will be 2, and the geometric multiplicity is the uh, number of linearly independent eigenvectors corresponding to a eigenvalue, because we haven't seen still that corresponding to one eigenvalue there can be two eigenvectors, but there can be also, okay, there can be more eigenvectors corresponding to one eigenvalue. There can be more than one eigenvectors also. So the number of linearly independent eigenvalues corresponding to the eigenvalue
is the geometric multiplicity of that eigenvalue. Okay. So we will see one example where or like geometric multiplicity is equal to, you can say also, dimension of the eigenspace corresponding to the eigenvalue. Okay. So we'll see some in example. Through an example we will understand what I mean. So let's say you have a matrix like this. So then how, first of all, we have to find the characteristic polynomial. Is determinant of so what is lambda minus lambda minus 9 minus lambda 8, that implies characteristic polynomial is this, and the polynomial equal to 0 will give you actually characteristic polynomial is this, up to this determine only this, but characteristic polynomial equal to 0 is giving you the will give you the root of the polynomial, and that those are nothing but eigenvalues. So here we multiply by this, what will happen? Minus of 1 minus lambda times lambda plus 5 is plus 9 and will be equal to 0. That implies lambda minus 1 times lambda plus 5 is plus 9 is equal to 0. That implies lambda square minus lambda plus 5 lambda minus 5, right? That's all. I mean, lambda square minus lambda plus 5 lambda minus 5 plus 9 is equal to 0. That implies lambda square plus 4 lambda minus 4 is equal to 0. Sorry, plus 4 is equal to 0. See, here also you will see lambda square plus 2 times lambda times 2 plus 2 square is equal to 0. That implies lambda plus 2 whole square is equal to 0. So eigenvalue is minus 2, and the algebraic multiplicity of minus 2 is equal to 2, right? The highest power in the characteristic polynomial is 2, corresponding to minus 2. So that's why the algebraic multiplicity is 2. And one important thing you always remember, the geometric multiplicity is less than equal to always algebraic multiplicity. Okay. So, and now how we find out the geometric multiplicity? To find out geometric multiplicity, we have to find out the eigenvectors. Okay, 1 minus lambda. There are two ways I will show you, but at least one way is this. One label by finding out the eigenvectors. 1 minus 9. 1 minus 5 x1 x2 is equal to negative 2 times x1 x2, right? So from there, what you get is this x1 minus 9x2 is equal to minus 2x1, and x1 minus 5x2 is equal to minus 2x2, right? From there, what you will get this from first equation, x1 minus, sorry, 3x1 minus 9x2 is equal to 0, right? And x1 minus 3x2, that is equal to 0. I think from both you get x1 is equal to 3x2, and any solution, like 1 3, sorry, not 1 3, 3 1 9 3, all these table will be solutions. So you take one of them as eigenvector. You can take eigenvector as 3 1, so this eigenvector will be 3 1. So in this case, you see that the algebraic geometric multiplicity. So it's only one vector. Another vector, whatever all other vectors are there, they are linearly dependent to this one. So eigenspace mainly is nothing but C times this 3 1, where C belongs to R. Eigenspace is generated by only one vector. Okay. So dimension of the eigenspace in terms of vector space is 1. So that implies geometric multiplicity is equal to 1. Right. So we found out the geometric multiplicity and algebraic multiplicity of two corresponding to one eigenvalue. So if you have a eigenvector, let's say if you have a matrix A, then you manipulate this A square, you can get a cube also, all these things. But can you, if you have a eigenvalue corresponding to A is lambda, then can you say something about the eigenvalue of A square? You can say about A square will be lambda eigenvalue, one of the eigenvalue will be lambda cubes. That's it. So for an, the eigenvalue will be lambda n. Also, if lambda is an eigenvalue, so lambda plus 1 will be eigenvalue for a plus I. Okay. Also, summation of eigenvalues, some properties I am telling you. Okay. Sum of eigenvalues is equal to sum of mean diagonal elements. You can check for this matrix, let's say 1 minus 9, 1 minus 5. For this matrix, the sum of the main diagonal is minus 4, right? And what are the eigenvalues? You have eigenvalues minus 2, and that is twice. So minus 2 plus minus 2, that is minus 4, right? So you can check for all those things, and the product of eigenvalues is equal to determinant of the matrix. Yeah, also one thing is, if A is invertible, A inverse will have eigenvalue as lambda inverse will be eigenvalue of A inverse. Okay, all those things you can prove. So let us prove maybe. So how we show that? If A has a eigenvalue lambda and the corresponding eigenvalue is lambda x, then Ax will be lambda x, right? And now A is invertible, so you multiply by A inverse on both sides. So to get A inverse Ax is equal to A inverse x, and lambda will come out here. So that implies uh, lambda, I mean x is equal to, because A inverse A is identity and identity times x will be x, that will be lambda A inverse x, right? That implies if you multiply now by lambda inverse and take this out, and first let's write A inverse x, that is x, and then lambda inverse multiply by lambda inverse, lambda is non-zero, let's say, then it will be lambda inverse x. So eigenvector, so eigenvalue corresponding to A inverse will be lambda inverse. Okay. So that's how we can show that for A square also. You will show A square times x will be lambda square times x. Even A n times x will be lambda n times x, and that is how eigenvalue, so lambda n becomes eigenvalue for A n. So there's a question like, let's say A is an idempotent matrix, then, and the order can be anything, then show that only possible eigenvalues are 0 and 1. Can you do that? How to do that? So what is an idempotent matrix? What is the definition of an idempotent matrix? Idempotent matrix definition is like, if A is an idempotent matrix, then A square should be is equal to A, right? So now what you see, now it's very interesting. So as lambda is an eigenvalue, lambda, let lambda be an let lambda the eigenvalue of A. Then there will be, then there exists x is not equal to 0. I mean 0 means 0 vector here, such that I mean x is an eigenvector, right? X will be an eigenvector, and then that will be ax is equal to lambda times x. From here, what you get if you multiply a by both sides. In the both side, if you multiply by a, this will be a times ax will be a times lambda x, which will give you s squared times x is equal to lambda times ax, right? Now you know that if s square is equal to a square is equal to a, that what does that imply? A square equal to a means ax will be equal to lambda times ax. That implies 1 minus lambda times ax is equal to 0. See, when if ax comes out to be 0, then it can be anything, but it is this, that is not the case, right? Lambda can be lambda, you see, for to make this sense, lambda has to be equal to 1, but the question is just telling that it can be 0 also, right? So how will you justify to that one? I mean, what will happen to that? So instead of doing in this way, let us do the another way. Okay, so first of all, you have this ax is equal to lambda x. So let us not do this. Okay, lambda x, and we know that if you multiply by a square times x will be lambda times ax. Again, in this, if you have ax, then what will happen? Lambda times lambda x, because from here that implies equal to lambda square x. Now from here, so what you got? A square x is equal to lambda square x, and here what you got? A times ax will be lambda square x, right? A square ax will be lambda x. Sorry, let me write it. A square x equal to lambda square x you got. So then, but what is this? A square is equal to a because of idempotent. So ax will be lambda square x, right? As a square is equal to a. What does that imply? Lambda times x will be equal to lambda square times x. That implies lambda minus lambda square times x is equal to 0. And here now x is not equal to 0, you know. He before that in this wrong one, ax is 0 or not 0, you do not know. But here you know x is not equal to 0. So lambda minus lambda square has to be equal to 0. That implies lambda times 1 minus lambda has to be 0. That implies lambda is equal to 1 or 0. And we started with a matrix which is idempotent. We do not know what is the order of that matrix. So it can happen that if A is a 4 by 4 matrix, then you can see that 0 0 0 0 are the, if it is idempotent, it can be 0 0 0 0, or it can be 0 0 0 1, or it can some other combination like 1 1 1 1, 0 1 0 1. It can be all other possibilities, but it cannot be like 0 2 3 1. It cannot be that's what I meant. But like if you have an idempotent matrix, you know that all the eigenvalues are either 0 or 1. Okay. So a good trick to find a characteristic equation for, let's say, for 2 by 2 matrix, it won't be true for 3 by 3 matrix, but it will be true for 2 by 2 matrix. For 2 by 2 matrix, shortcut for characteristic equation is you take lambda square minus of, you add this to the diagonal a plus d times lambda, and you make plus of ad minus bc. I mean, this is the determinant of c, and that you know that from the school level algebra, this two will be nothing but addition of the root, negative of addition of this root, and this one will be the product of roots, right? I mean, what I mean, this lambda square, x square minus x square plus ax plus b. If this has root, say x1 and x2, then what? How you can write x square minus x1 plus x2 times x plus x1 x2 is equal to 0. You can always write like this, and that implies this. You can x1 minus x1 plus x2 will be a, x1 x2 will be b, right? So that is how, let's say there is a question. I will be writing the question. The product of two eigenvalues of the matrix A is equal to 6 minus 2, 2 minus 2, 3 minus 1, 2 minus 1, 3 is the product of two eigenvalues of the matrix A is 60. Find the third eigenvalues. So you may pause the video for some time and think about it and then do, okay? So the answer will be like we have already mentioned, I have mentioned already something, that if you have eigenvalues, the product of eigenvalues will be determinant, right? So what, and two things we have done. So we can do the answer in two ways. So one way is, you know, lambda 1 and lambda 2 and lambda 1, lambda 2, lambda 3, let's say, are three eigenvalues. So what is given? The product of two eigenvalues, lambda 1, lambda 2 is equal to 16. And we also know lambda 1, lambda 2, lambda 3 is equal to determinant of this matrix. That's the hint. I mean, that is the hint of this thing. I mean, the question, this question. Okay, so then what will happen? This one can write as lambda 3, the third eigenvalue, will be determinant of A over 16. Whatever the answer. So determinant of A you can find out. Determinant of A, it's given, a matrix is given, so determinant you can find out. You will see that determinant will be 32, and if you do that, that's another eigenvalue you can find out. So given two eigenvalue, you can find out another eigenvalue if you know the determinant only. So you don't need to do all the calculation, because in this case the in this case the characteristic polynomial will be also like a third degree polynomial, right? Yeah. So now another thing is something called Cayley-Hamilton theorem. So the Cayley-Hamilton theory. What it says, the matrix will satisfy its characteristic polynomial. What's the meaning of that? So every like square matrix will have a characteristic polynomial. So if you have a matrix A and the corresponding characteristic equation is, let's say, lambda to the power n plus a n minus 1 x sorry, lambda to the power n minus 1 plus up to a naught is equal to 0. If this is the characteristic equation, then according to Cayley-Hamilton theorem, A will satisfy the characteristic equation, mean a to the power n plus a small. These are some constant coefficients. A to the power n minus 1. I mean a n minus 1 plus up to plus a naught times nothing means identity matrix, that is equal to will be a zero matrix. This is what Cayley-Hamilton theorem says. You can say that what is this? I mean, we will see while using this. I mean, what I would say, if you have a matrix like this, let's say you have a matrix like this, A is equal to 1 0 2 1, right? Then what will happen? Lambda square minus the characteristic equation, lambda square minus 2 lambda plus 1 will be equal to 0. So don't take this one, maybe some 2 1. Okay, so then it will be lambda square minus 2 lambda minus 1, right, equal to 0. That implies, so that implies it says that Cayley-Hamilton says that A has to satisfy a square minus 2a minus identity is equal to 0. One can check also here, verify that what is a square. A square will be 1 1 2 1 and 1 1 2 1. If you multiply that, let's write here, that will be 1 sorry 3 2 4 3 and minus 2a, I mean plus 2 into identity, that will be 2 2 4 2 and minus plus identity matrix, if you add, that will be plus 0 1 sorry 1 0 0 1, that is nothing but 3 2 4 3, right? Now if you take a square minus 2a minus I is nothing but a square minus 2a plus I, and that will be zero matrix because this and this, they are equal, you can see, right? So Cayley-Hamilton theorem says that this has to satisfy, and that's what we just checked for a simple example, that way that it follows from the what Cayley-Hamilton theorem says. So now, so for this case, I might be, if you know this A inverse exists. See, let's, your matrix is this 2, I mean 1 1 2 1. Okay. So in this case, it will be easy to find out A inverse. Still,
what we see that the A inverse exists, but how to find out A inverse using this Cayley-Miller theorem? So what do we do? This A square minus 2A plus, minus identity equal to 0 matrix, right? That implies if you multiply by A inverse times A square minus 2A minus I, that will be A inverse times 0 matrix. That implies A inverse times A times A, that is A square minus 2 times A inverse times A minus A inverse times identity is will be 0 matrix. That implies this will identity. So A minus 2 identity will be A inverse. So to find out A inverse, you don't need to go to anywhere else. You just find out this quantity, then it will be. Then you are done. I mean, the thing is, using Cayley-Hamilton theorem, we don't need to find rigorously the way you knew that how to do the how to like using adjoint and determinant, all this thing you no need to do. You just take A and subtract that from 2 times identity. I mean, it depends on the matrix, but yeah, for this matrix it is A minus 2I, and you got the inverse of the matrix, right? So we'll see in this one. Let's say you have A is equal to, for a bigger matrix, 2 1 2 5 3 3 and minus 1 0 minus 2. How do you find the inverse of for this one? So first of all, try to find out the characteristic equation. Then the Cayley-Hamilton theorem procedure. Let's say procedure. First, characteristic equation. Second, use Cayley-Hamilton theorem. CH theorem. 3. Multiply by A inverse if exists, because in this case it will exist because it is asking to find out A inverse, right?
Yeah, so let's start. So this A matrix, you can find out the characteristic equation, right? This is like for to find the characteristic equation, you may have to find the determinant of A minus lambda and make it to 0, right? That's what we do. So when we do that, I mean that will implies 2 minus lambda 1, 2, 5, 3 minus lambda 3, minus 1, 0, minus 2 minus lambda. That is equal to 0. That will give you can find out that this will be lambda cube plus 3 lambda square plus 7 lambda plus 1 equal to 0. So you just check it, okay? Check. Then what will happen? This Calibrator theorem says that theorem it will happen to happen that A has to satisfy this, means A cube plus 3 times A square plus 7A plus identity is equal to 0. Zero mean here zero matrix. That implies now you multiply by A inverse, right? Then what will happen? This minus of A inverse times A cube, which will you can write as A times A square plus 3A inverse A times A square, you write it like this, plus 7 times A inverse A plus A inverse times identity is equal to 0. That implies give A inverse times identity, which will be A inverse, will be equal to this quantity will go that side, which will give you A square minus 3 times A plus minus 7 times identity. So only what you need to find A multiply again by A. So A square if you find out, find A square. Then you know A also and 7 arithmetic. You know all these things. So you just then calculate A square minus 3A minus 7 identity, which is inverse of the matrix. See, for a 3 by 3 matrix, it becomes like in another different way you can find out the inverse of the matrix without going by adjoint and all. So we'll see here one example where you will see corresponding to one eigenvalue, there can be two eigenvectors. So that is a matrix. Let's say a matrix is given by 7, 4, minus 4, 4, 7, 4, minus 1, minus 1, 4. This is a matrix. So lambda is equal to 3 will be one eigenvalue that's given to you. Let's say given to you that lambda is equal to 3 is an eigenvalue for this matrix. Now find out the corresponding eigenvectors. Just I want to show you that there exist there can be two eigenvectors. Two in the sense that see always there exists infinitely many solutions, but the solutions are linearly dependent. But in this case, you can find out two linearly independent eigenvectors, and you will see that this geometric multiplicity will be 2 in this case, corresponding to one eigenvalue. If you can show maybe that for this eigenvalue, algebraic multiplicity 1, but the geometric multiplicity is 2. Sorry, algebraic multiplicity. See, the algebraic multiplicity has to be then 2, right? Because if you know the algebraic multiplicity is bigger, so algebraic multiplicity has to be greater than or equal to 2. right? If this corresponds to these three, you get two eigenvalues which are linearly independent. Okay, so let's find out what will be the eigenvector. Times you have x1, x2, x3, which is to be equal to 3 times x1, x2, x3. From here, what you can write from here, sorry, from here, what you can write 7x1 plus 4x2 plus x3 is equal to 3x1, and 3x1 you take here, this will be 4x1 plus 4x2 minus 4x4, right? Sorry, minus x3 is equal to 0. And for you can see that for all the cases, I mean for three equations, it will be like the same. Okay, so when this is like this, so what you can write is x3, you can write as 4x1 plus 4x2. You cannot simplify more, right? So what happens here? You have got two values which are independent, which are free variable. When x1, x2, any value you take, you will get another x3, and that will be a solution of the system. And what we will, how we will see that the eigenvectors are, it was x1, x2, x3. So, but if you write this x1, x2, x3 as, it will be x1, x2, and 4x1 plus 4x2, right? From here, what you can write this, you can write as x1 times 104 plus x2 times 014. And what you can show that these two, and I mean this will be in the eigenspace. I mean 104 is also eigenvector. 014 also eigenvector correspond to same eigenvalue 3, correspond to one eigenvalue, then an eigenvector vector. Also, any linear combination of these two will be eigenvector. They are linearly independent also, right? So in this case, the eigenspace dimension of the eigenspace is 2, because they are, that is generated by two vectors which are linearly independent, and that's why the geometric multiplicity of the eigenvalue lambda is equal to 3, that is eigenvalue 3 is 2, right? So the algebraic multiplicity you can show that is will be at least have uh, that will be at least will be 3. Okay. So we'll do few more questions here. I mean, if I don't have place to write, maybe here I will start. So the question is here, A is equal to 2 minus 1, 3, 0, 7, 4, 0, 0, minus 5 is a matrix. Find out the eigenvalue of A plus 6i. This, if you have remembered, then it will be easy. If you remember that how, like I told this one, right? So how to evaluate this eigenvalue for this matrix A plus 6i, right? So if you know the eigenvalue of A, can you say something about A plus 6i?
So what people may try that you just add 6 with the diagonals and then try to find out them. So, but that don't need to do because to add those 6 in the diagonals again, it will the computational time will be like they will have to spend more time to calculate. It will be more calculative. So instead of that, you find out the eigenvalues of A. So if you find out the eigenvalues of A, you can show that eigenvalues of A are 7, 2 and minus 5. So eigenvalue of A plus 6i because an eigenvalue of 6i are 6, 6 and 6. So eigenvalue of A plus 6i will be 7 plus 6, 2 plus 6, minus 5 plus 6. So that implies 13, 8 and 1. See how easy it became. So if you want know the eigen value of A, then A plus some k times I also, A plus k times I for this matrix also you can find out the eigenvalues. Very easy. Just add the eigenvalues of A by k, add by k, okay, then it will be the eigenvalues of A plus k times I, okay. Having the lambda plus k is eigenvalue for A plus ki if lambda is eigenvalue for A. So the question is, can you say it for any A plus B? So check it. It is a homework. Say you have A and B two matrices, and you know the eigenvalues for both. Can you say that the eigenvalues of A plus B are nothing but the eigenvalue summation of the eigenvalues of A and eigenvalue of B? Can you say that? That is the homework for you. So now we talked about once about the diagonalization. In how we diagonalize matrix. We'll see in a small question. I mean, a very easy example that how one can like after diagonalization whether you can diagonalize exactly the matrix whether you can diagonalize, right? So let's say you have a matrix A. Okay, A is -1, 4, 3, -2. So you can show that this lambda, the characteristic equation will be lambda square plus 3 lambda 0. And if you solve it, lambda will be 2 and -5. right? So the eigenvector corresponding to these two, what you can show, you can find out the eigenvectors. So corresponding to -5, corresponding to -5 eigenvector will be -1 and 1, and corresponding to 2 the eigenvector will be 4, 3. So then you find the matrix will be -1, 1, 4, 3. You just take a matrix like this, and if you, what we saw that P inverse AP should be a diagonal matrix, right? So if you here, if you multiply and you find out P inverse, that will be 1/7 -3, 4, 1, 1. So we'll calculate this one. Okay, we'll calculate it on the page. Let's say here we'll calculate. The P inverse was 1/7 -3, 4, 1, 1. A will be -1, 4, 3, -2. And P inverse AP, P again is -1, 4, 1, 3, right? So now let's multiply. So 1/7 will be as it is. So then, so this one will be 3 plus 12, right? 3 plus 12 and -12 minus 8, -12 minus 8, -20. Okay, so let me write it properly then, I mean in a compact way. So it will be, first one will be 15, then it will be -20, it will be 2 because -1, 3 minus 1, it will be again 2, then -1, 4, 1, 3. So that implies -15, -20, 1/7 times -15 -20 -35. 60 plus 60 is 0, it will be 0, 8 plus 6 is 14, so which will give you -c, it becomes diagonal. The matrix I started, which has two distinct eigenvalues. So two distinct eigenvalues for the 2 by 2 matrices, and we show that corresponding to two eigenvalues, there will be two eigenvectors which are linearly independent, and you constructing a matrix arising from the eigenvectors, we could show that P inverse AP is a diagonal matrix. So that implies the matrix we started, that is diagonalizable. And now if you want to find out, let's say you have A, you want to find out A to the power 100. So A to the power 100 will be P inverse P inverse AP to the power, it is P inverse P dP inverse. See, let's say you have P inverse AP is equal to a diagonal matrix. That implies A will be like the from this P dP inverse, right? And now if you take A square, that will be P dP inverse times P dP inverse, and this two will vanish, and then you will get P d square P inverse. So similarly, you will get A to the power 100. If you want, they are asking to find out A to the power 100, then it will be P times D to the power 100 and P inverse. And D to the power 100 calculating is very easy because those will have diagonal element like this. So you just take -5 is there, so you take -5 to the power 100. So that will be 5 to the power 100. So and then you multiply by p and p inverse, you get a to the power 100. Instead of multiplying 100 times a, if you multiply 100 times a, that will be more difficult, right? So d to the power 100 will be easily you can find out, and if then multiply by a p, and they multiply from left side by p and right side by p inverse. Then see what done by then you are done, right? So you can find out if they ask for power like a to the power 100, find out a to the power 100. So you can diagonalize first and you can do it this way, right? Yeah, so we are in the end part of the session. So almost all the things are covered, including diagonalization. I mean, from the
from determining eigenvalues and eigenvectors, so you know how to get the diagonal matrix. I mean, if it is a diagonalizable matrix, which the like that is corresponding to which matrix you can find. I mean, when something you get like P inverse AP is equal to B, some other matrix, then we say these two matrices are similar. Okay, so that's why it is. I mean, P has to be some non-singular matrix. Okay, that is the rest. So in this case, when you saw that P inverse is equal to a diagonalized matrix, so mainly and diagonal matrix, mainly the matrix is similar to a diagonal matrix, and thus the matrix is diagonalizable. Okay, so if you have a two like for two by two matrix with two distinct eigenvalues, you consider the matrix is diagonalizable. So for A, which is n by n matrix, if you have n distinct eigenvalues, you consider that A is diagonalized. Okay, so those are some easy observations, but which you can use in your assignments and all. I mean the questions, some questions. So there are some theorems, like if you have a symmetric matrix, sorry, I mean if you have a Hermitian matrix, the root of the Hermitian matrix will be always real. Okay, so that you remember. So because this AX, I define our Hermitian matrix mean AX is equal to lambda x you have. Now A star is equal to A because it's a Hermitian matrix. From there what you will get, lambda is will be lambda bar. And lambda is lambda bar, lambda is real number, means lambda has to be, sorry, lambda is any number, let's say, and the lambda is equal to lambda bar, then what does that imply? That implies that your imaginary part is 0, that implies lambda has to be real. Because why we are saying this? Because for real matrix also you can get complex eigenvalue. How? Let's say you have equation like this. Okay. 0 minus 1 1 0, this is a matrix. So then what will be A minus lambda? Determinant of A minus lambda will be minus lambda minus 1 minus lambda equal to 0. That implies lambda square plus 1 is equal to, that implies lambda has to be plus minus identity, right? So for a real matrix also you can get complex eigenvalues. But what it is telling, that whatever the matrix, like if the matrix is Hermitian, then the eigenvalues has to be real. The eigenvalue, all the eigenvalues are real. Okay. So the one another observation is all the reflection matrix. I showed you what is the reflection matrix. I mean you can more generally you can take cos n theta sin n theta and cos n theta sin n theta minus sin n theta minus cos n theta. This matrix you can show that this is diagonalizable. This uh, this is a reflection matrix mainly. So you reflect a point by n theta. So then it will be, when you want to reflect it, you just multiply by this matrix. So most of the things are done. I'm looking for something if I can do for you. I mean, otherwise we can stop today for today. Yeah, so we are done for today, most probably. So at least what you can take up from today's session is how to find out, mainly how to find out the eigenvalue and eigenvectors. So, and how to diagonalize a matrix, which we started with, like which we started with the beginning, that by telling that we will discuss these two. So almost all the things are done, and also your uh, the questions from the assignment also, those are also I have done almost all the questions, so I think it will be okay for you to, like, it will be, you can easily solve those questions by yourself, and you will watch this video. This will be recorded, so I have recorded this, I will post in the YouTube, so you check that, and you, if you have any question, you ask me through an mail or the discussion forum which you have in the NPTEL in NPTEL website. So you can use those. Okay. Yeah, I think. Yeah, so we can end the session, today's session. So before ending, so these are your reference references, book and references. And yeah, so thank you for your attention, and we'll end the session.